We're going to be determining the strength of acid and base. How do we know if a particular compound is strong acid? How do we know if it's a weak? How do we know if it's a strong base and or weak base? And we can look at several different ways in order to target whether this particular compound is a weak acid or even if it's an acid at all and base. The very first thing that we want to look at is the dissociation in water. Will this compound dissociate in water and how much of it? For example, if the acid, like HCl, completely dissociates all or most of all of the hydrogen and chlorine they have split apart into in water, right, in water, then we know that we consider that acid as strong. If only some has broken apart, but some hasn't, so less than 100%, so maybe 50%, maybe barely any has broken apart in water, then we consider that particular acid weak. And that goes same for base. Say a base, this is NaOH is a base, and the OH completely dissociates from the sodium. Whereas here, H2O, the hydrogen, as it dissociates, NOH minus is formed. This is less than 100%, then we consider that as a weak base. So in other words, we can say that in a strong acid, we know that, or base, it will completely dissociate in ions, 100% of the molecules, meaning that if you look at these arrows, will go into this direction, meaning that it's only going to go in that direction. Very rarely it's going to go into reverse. And same for sodium hydroxide. This is your base here forming into hydroxide here. Now, if it's a weak acid or base, you'll notice that only partial of the ions will dissociate into ions and only some of them will stay intact. For example, this is an acetic acid. An acetic acid will go into split form, but it can go reverse direction, making up back into the acetic acid. So not every one of the molecule will break apart. And even if they do, they will reform again. A second way to know if a compound is a strong, weak acid or base is by knowing its chemical knowledge. What that means is really just knowing it about the chemical in itself. Here are the list of strong acid. HCl, HBr, HI, HClO4, HNO3, H2SO4. Now, if it's not on this list, then you're going to assume that they are weak. You will find in your reference sheet this particular list of strong acids. The only note over here is that I want to indicate that there is no HF. A lot of the people think that because Cl, Br, and I, because it follow under the halogens, they automatically assume that HF is strong acid, but this is not the case. This is actually a weak acid. So having this reference sheet in handy will let you know if you have a weak acid. So if it doesn't fall under here, then it must be weak. If it does, then it is strong acid. And that goes same for base. So if it falls into group A metal hydroxide, like lithium hydroxide, so group 1A refers to that first row of the periodic table, and then also the second row, but not just any one of them in the second row, but calcium and down. Let me show you the periodic table to help us get that shown, okay? So here is lithium and down. So all of these guys, even all the way to the F, these guys will have lithium plus the hydroxide, so lithium hydroxide, right? So something like this would be a strong base and all the way down. And then from calcium and all the way down, okay, these guys with hydroxide would be considered to be a strong base. On everything else, you're going to assume that they are weak, including NH3, that is a weak base. Here's another chemical knowledge that you should know is that if you look at on this chart, HCl, we know that based on the previous slide, we know that it is a strong acid, but look at its counterpart, meaning this is your acid, then this is its conjugate base. And if the acid itself is really strong, its conjugate base is going to be weak, like HCl. For example, the stronger the acid, so HCl, this is a very strong acid. This is strong, so that means that its counterpart will be a weak base. This is strong acid. So what if you have something like this, a weak acid? HPO4 2 minus, okay? So this would be weak acid. That means its counterpart, the conjugate base, which is PO4 3 minus, it is strong base. I want to say strong, but it's much stronger than some of the weaks that we see. Now, stronger the base is, so if we have a very strong base, the conjugate acid will be weak. So for example, here's my hydroxide, which is a very strong base. We've seen a lot of hydroxide being strong base. That means its counterpart or its conjugate acid is going to be weak acid. So we know that if one is stronger, its counterpart is going to be the weaker one. So that's for the chemical knowledges. And what about some other ways? Another way would be to measure the pH. If the pH falls under between 1 and 3, it indicates a strong acid in the solution, or the pOH falls under I would say the opposite direction, so 11 through 14. But here I'm only giving you pH to give you some more clarity, and I'm going to be referring to pH more often. What if there is very high value of pH, 11 through 14? That indicates very strong base. Whereas a weak acid and base, for a weak acid, it will fall under 4 to 6, and then it will for a weak base, it will fall under 8 and 10. So for example, if I were to have a scale of 1 to 14 here, okay? 1 to 3 for pH, this would be my strong acid. Whereas 11 through 14 will indicate a strong base. Anywhere between 4 to 6, this would indicate weak acid. And here's my neutral, that's at 7. And then anything between 8 and 10 would be a weak base. Okay? Would you say 10 exactly is a weak base? What about 10.2? It just sort of depends, but this is a general idea of how we can determine the relative strength of acid and base. Another way to do this is to look at the Ka and the Kb values. Well, what is Ka and Kb? Ka refers to the equilibrium constant for an acid. Remember, the equilibrium constant for water was Kw. Equilibrium constant for any other substance were considered to be Kc. Here, if I'm looking for equilibrium constant for an acid, we consider that as Ka. For example, say we have an acid in solution, and in that solution, it's going to react with water, Okay, so H2O here. And that water forms into H3O plus because acid has donated its H. So now they're hydronium ion. The acid has lost an H, so it has A minus right here. So if I were to put this into the equilibrium constant, we have the product, which is the hydronium ion and the conjugate base, over the acid in itself on the bottom. We don't include the water since it's liquid. So if I were to compare this value, if I were to solve this out and look at the Ka, we can determine whether this particular substance has a strong acid or base, or a strong acid or weak acid. A very large Ka value indicates strong acid. So what is large? Anything 1 or greater would be considered large. If it's less than 1, then it's considered to be somewhat of weak acid. Here's another way to look at the Ka value. So instead of solving it out, you can actually look at the actual Ka values. This is in your reference sheet as well. Notice these are all actually all weak except for this one. It's a strong acid. It means that it's probably the value of the Ka is really, really high. Here, let's do a learning check based on this Ka value. Which of the following acid is stronger? They're both weak acid, but which one is stronger, right? And I'm not saying that this is a strong one, but which one is the stronger one. You'll notice that the Ka value for hydrofluoric acid is greater in value, not just because they're 6.8, but it's 10 to the negative 4, right? That's less decimal compared to acetic acid. So we know that this one is the weaker. Let's see. Oh, I apologize. This is the stronger. Acetic acid. And this is the weaker. Stronger acid. Weaker acid. Next learning check, it says acetic acid is the principal ingredient in vinegar that provides its sour taste. At equilibrium, a solution contains, this is the acetic acid, it gives you the concentration, also it gives you the concentration of the hydronium ion and the conjugate base. What is the value of Ka for acetic acid? So for this, you're going to need to set up the molecular equation in order to sort of organize everything together. So acetic acid has this acidic component when it's submerged in water. So it's going to be submerged in water, H2O liquid. And if this is the acid, then we need to donate the hydrogen to water. So if it donates this, then this acetic acid counterpart or the conjugate base becomes negative, and that hydrogen has been taken out. Plus H3O plus. So these are all aqueous on the product side. So you'll notice this pattern. You have an aqueous acid or base, and there's water, which is going to be liquid, and then you have the rest of the equation indicating aqueous. All right, so Ka is concentration of the conjugate base, hydronium ion, and then all over the CH3CO2H. And it wants to know the Ka value, and it gives you a bunch of other values on the top. So let's go ahead and plug in the values. This is 0.00118 times 0.00118, then divided by 0.0787. So pause this video and see if you are able to calculate this out. Coming back, the calculation should show that this is 1.77 times 10 to the negative 5. So what does that mean in terms of the strength? Is this a weak acid or a strong acid? It's less than 1, definitely. So this is considered to be a weak acid. Now let's look at Kb, since we've looked at Ka. Kb looks at is the equilibrium constant for a base. So here I have a base, okay, Aq. It is submerged in water, H2O, and it has the ability to accept the hydrogen from the water. Okay, so it's accepting the hydrogen, and the water becomes hydroxide. So you see the Kb value or Kb setup has the product, right? The product over the reactant. So we have the reactant here. And very similar to the Ka, if the Kb value is high, so greater than 1, we can say so the substance is a very strong base. If the value is less than 1, then we can say that this particular base is weak. And also in your reference sheet, you should see a common base with its Kb on the right. And so I will be utilizing this in your homework and also in problems. So if you were to refer back to what the Kb's are. And if you look at all of these are a weak base. They're all less than 1. Let's do a learning check based on that base. What is the equilibrium constant for ionization of HPO4 2 negative ion, a weak base? And it already gives you a nice equation that goes with it. If the composition of the equilibrium as mixture as follows, so it gives you hydroxide concentration, the P2PO4 negative concentration, and also the the equilibrium value for the PO4 to negative value. So we're going to set this up. Let's see. Kb, we know that Kb is equal to the product plus or multiplied by the other product, which is hydroxide, divided by the reactant. And we ignore the water since water is liquid. So let's plug in the values. 0.042. Hydroxide is 1.3 times 10 to the negative 6 all over 0.341. Okay, so you're going to punch this into the calculator and come back and check the key. And here is the key.